We are seeing concepts in the chemical equilibrium, and this video is about one of the components of the equations that we have looked at, and that's the standard reaction Gibbs energy. Alright, the most important expression in all of this chapter is this one, which simply tells you how you can calculate whether the process will be spontaneous or not, a chemical reaction, if you know what the reaction Gibbs energy is at the standard state, and then if you know what the concentrations or the partial pressures of the species involved are. We also have seen that this expression at equilibrium turns into the following. Delta RG naught is equal to minus RT natural log of T, K, or the equilibrium constant is equal to this dependence on the reaction molar Gibbs energy. Okay, at the standard state. Right, so again, something that you need to do all of these calculations is the reaction molar Gibbs energy at the standard state. Remember that the standard state is defined as gases having a pressure of 1 bar, and then the concentration of solutes would be 1 molar. Now, the question is, well, how do we get those numbers? And the way that we actually have been doing this until now is as follows. This reaction Gibbs energy can come from calculations of the reaction enthalpy and then reaction entropy, and all of these data are at the standard state, which usually appears in tables. Now, this works well, and this is the way that we have learned to calculate the reaction Gibbs energy, but it looks fairly tedious, right? First you have to calculate the reaction enthalpy, then you have to calculate the reaction entropy at standard state, and then make sure that the units are consistent and carry out the calculation. What we actually do in this video is introduce an easier way, a more direct way to calculate the reaction Gibbs energy, in which you don't have to evaluate these two values. Right. So one of the things that you have to think about is that the Gibbs energy, okay, because it depends on the enthalpy and the entropy, and those are state functions, is also a state function. Okay, again, the reaction Gibbs energy is a state function. So for a chemical reaction like A to B, right, we can actually say that, or more generic if you want, reagents to products. Okay, we can say that the reaction Gibbs energy would be equal to the Gibbs energy of products minus the Gibbs energy of reagents, okay, at the standard state. The way that we do this, this is the same way that we have done this for the enthalpy and the entropies. Okay, that would be the sum of some measure of the molar Gibbs energies of products minus some measure of the molar Gibbs energies of reagents, where these are just the stoichiometric coefficients that are modifying the reagents and products. Now, when we were looking at enthalpies, we actually had a very similar recipe for this. Okay, but notice that in the calculation of the enthalpies, we said that, well, we actually don't know what the absolute enthalpies would be for a species, and then we had to use something that was called a relative measure of the enthalpy, which was the enthalpy of formation. Right. So the way that we actually used these expressions was using what we call the enthalpy of formation of products, which is a molar quantity, minus the sum of the enthalpy of formation of reagents, which was also a molar quantity. And again, all of those are at the standard state. Okay? Matches this and that. Now for the entropy, we actually did something different. Okay, for the reaction entropy, what we actually did is utilize something that was called the absolute molar entropies. Okay, and that's because we can calculate what the absolute molar entropy is for a substance, unlike the enthalpy, by using the third law of thermodynamics, which indicates that the entropy of a crystalline substance at 0 Kelvin will be 0. Okay, so notice that there's two different types of variables that we use in this expression. For the enthalpy, we use the enthalpy of formation. For the entropy, we use the absolute molar entropy. So the question is, well, which one of these are we going to be using for the Gibbs energy? Well, the Gibbs energy is an energy, all right, much as the enthalpy is also related to an energy. Okay, so it's impossible for us to know what the absolute value of the molar Gibbs energy of a substance is. Instead, we're going to have to use a relative value, and then every substance will be referred to that the same reference, and that will allow us to be able to calculate changes to the Gibbs energy again with those relative values of the molar Gibbs energy for all of the substance, as long as they are referred to the same reference. And it turns out that the reference that we're going to be choosing to set the zero for the molar Gibbs energy is the same one as the alpha p. Is going to be would be what we call the molar Gibbs energies of formation. Okay, so just to remind you a little bit of what those formation processes are, what we're going to say is that the most stable allotropes of constituent elements are going to have a molar Gibbs energy of 0 at the standard state. Okay, so the atoms that we're interested in this course are going to be H2 and or hydrogen, and H2 is the most stable allotrope. Then oxygen, the most stable allotrope of oxygen is O2. For nitrogen will be N2, and then for carbon will be graphite. Okay, and for all of this, we're going to have values of the Gibbs energy of formation molar at the standard state. By definition, they're all going to be 0. Okay. Now the question is, well, how do we figure out what the Gibbs energy of formation of any molecule that is not the most stable allotrope of an element, what those values are going to be? Again, remember that the way that we do this is we set up the reaction of formation of that molecule that we might be interested in, like say CO2 or water, from the most stable allotropes. Okay, so let's think about the reaction that forms water from H2, which is a gas, and O2, which is a gas, and we're going to do this at 298 Kelvin and 1 bar of pressure, which generates liquid water. Right? So when we actually use this expression, but instead of putting here the absolute molar Gibbs energies, we agreed that we're going to be using the Gibbs energies of formation. We can calculate the Gibbs energy of that reaction simply as follows. Delta Rg for this particular reaction is going to be equal to the Gibbs molar Gibbs energy at standard state for the product, which is going to be this, the molar Gibbs energy of water, which is liquid, the standard state, minus the molar Gibbs energy of reagents multiplied by the stoichiometric coefficient. So that will be the molar Gibbs energy of H2 gas at the standard state minus 1/2 times the molar Gibbs energy of formation of O2 at the standard state. But again, notice that by definition, okay, this number is 0 and that number is 0. Okay, so if there's any way that we can measure the molar Gibbs energy under these conditions, 1 bar of pressure for each one of the gases, then we will actually have directly what the value of the molar Gibbs energy of liquid water would be. Another way to actually calculate this number is to then use delta R H naught minus T delta R S at the standard state. Right? This one we can calculate from tables, which will give us the reaction Gibbs energy for this reaction, and that corresponds directly to the Gibbs energy of formation for liquid water. Proceeding this way, we can actually then obtain the Gibbs energies of formation for any single species that we want. For CO2, we'll set up here the same reaction, but the product will be CO2 gas, and then the reagents will be O2 gas and graphite. And for glucose, you would have the reaction of formation of glucose from graphite, hydrogen, and oxygen. And again, proceeding this way, you can find what the Gibbs energies of formation are for any species that you want. Then what happens is we collect all of that data, we put it in tables, and we're going to have tables in books or online where you actually are going to have again the value of the Gibbs energy or formation for a variety of species at the standard state. Okay, and again you have all of those values in kilojoules per mole. Okay, so your book contains a table with the molar Gibbs energy of formation. Again, those are very advantageous because they allow you to compute very easily what the Gibbs energy of a reaction is at the standard state, and this value is very useful because then you can go on to calculate what the equilibrium constant is, or maybe to carry out the calculations of the prediction of whether a reaction will be spontaneous in the forward or reverse direction. Okay, so that is again our new definition of, or a short way, a shortcut to calculate what the reaction Gibbs energy at the standard state is.